Hello, and welcome to the module From Idea to Verified Hardware. In this module, we'll be going over a couple of topics. These include breadboard basics, how to translate a schematic into hardware, as well as some basic troubleshooting tips. We'll also discuss what results you should take once you have a fully functioning piece of hardware. We'll use breadboards to prototype most of our circuits. Breadboards are split into two symmetrical sections. They have a left side and a right side. Each side has a voltage rail and a ground rail running vertically along it. It's generally useful to simply connect this voltage rail to one of your red connectors and this ground rail to one of your ground connectors. You can then also jump across from one side of the board to the other to make sure you have power and ground available on both sides. Note that the two voltage and ground rails are not connected to each other. That is, the left side is not connected to the right side. Once you've connected your board up like this, you can simply plug your power supply in to each of the two terminals to make it fairly easy. When you're placing components on your breadboard, place ICs in the center. They'll fit nicely across the two rows. Additionally, make sure that you're not forcing wires into your breadboard. Wires should insert only a couple millimeters. If you force them in further, they can short to other rows under the board and cause issues. On the same note, make sure your wire is long enough to go into the breadboard. If it just barely sits in the hole, it's probably not making a connection and will cause you trouble debugging later. Let's take a look at a fully finished breadboard and see what we like and don't like about it. Immediately, you can see that we've got a power rail on top and a ground rail. And you can see we have short jumpers to all of our other power and ground rails. Additionally, everywhere that we've jumped off of our power and ground rail, we've inserted a decoupling cap, as you can see here. That's good standard practice and should always be followed. Looking a little closer at some of our ICs, you see they're placed across this center divide. Additionally, each IC has a decoupling capacitor attached to it. These decoupling capacitors go directly from the power of the chip across to the ground of the chip, and they're placed right next to it. You can also see that we have resistors whose leads we've snipped so that they're not long and waving around in the air. You can see some of them over here. We've also got a diode where we've snipped the leads. Try and keep all leads as short as possible, as it'll remove noise and make things generally easier to work with. Here we have a couple of components placed right next to each other. This is a very tight area on our breadboard, and so we didn't have room to insert a bunch of extra wires. And so we used the leads of our components to serve as the wires. For example, we didn't have to jump this with a wire over here and then place the resistor there. We simply extended the wires of the resistor and placed it right there. Notice how we've made sure to keep ample space between any of the bare wires on the resistor and this lead coming from our capacitor. One common source of issues for new students building breadboards is that the bare leads on resistors will touch each other and intermittently short out your circuit. Try to avoid this, so just be very careful about it when you're first building. Here we have another close-up shot of a different place on the breadboard. You'll see in this shot we have a couple of wires which have to jump long distances to other parts of the board. If you have to jump long distances, custom cut a wire to go the correct length. Don't use an extremely long wire and loop it around in the air. Simply cut one to be the desired length. Again, you can see we have resistors whose leads we'd cut so they're not dangling around in the air. And we have decoupling capacitors on all of our ICs. Make sure that these are always included. So here we have an example schematic. We've worked with this one before. Let's go through how we might translate this into a breadboard layout. The first thing we notice is that we're going to have two integrated circuits. We have two ICs here. And then we're going to have a couple of inputs as well as a voltage supply. And we're in fact going to have two different voltage supplies. If we lay this next to our breadboard, the first thing we do is take a look at the data sheets for these two ICs. We need to know what their pinouts are before we can do anything useful. In general, you can simply place the two ICs down in the middle of your breadboard and start working. Here we'll have this lower IC be our op amp and this upper one be our 555 timer. Make sure you include your decoupling capacitors so we can place those on immediately. You can either add a short jumper to another row and place the capacitor there. Here we have a little capacitor. Or you can simply use the capacitor leads itself and place it directly across the chip. Since we have two voltage supplies, we have a 4 volt and a 12 volt needed, we'll simply use one rail for each. We can connect this side up to 12 volts and this side up to 4 volts. Additionally, we have our input signal, so we may just add a stray wire coming off which will connect to our function generator. We can now connect our two ports up to our power supply, and we're ready to start building the rest of the circuit. Before you start placing any of the other components on, think about how many components touch each node of your circuit. For example, if we look at the discharge pin here, we'll see it's got one connection to a capacitor, one connection to a resistor, and one connection to another port on the board. So when we build it, we're expecting 3 holes to be taken up on that row. You can see it's this pin, so that corresponds to this row. So if our circuit was built correctly, we should have 3 of these taken. You can count how many connections each node has to help you debug your circuits. When you start troubleshooting something that you think should be working, always begin at signals that you know what they should be. For example, test your power supplies. Do you actually have the right voltage, and are grounds actually 0 volt? Also, check your input signals. You should know what your inputs look like, so just make sure that they're getting to the right place. When you're checking these values, don't simply check the voltage rail or the ground rail over here. You can see that this top IC, the power should be connected to this pin, as we have a power jumper right there. So actually use your scope probe, place it on that pin, and double check that you're getting the correct input signal. Once you've checked that all the input signals are correct, take one step forward in your circuit. That is, if we've checked on this op amp down here that all the input signals are what we think they should be, check the output of that circuit. Don't immediately jump to the output of the complete schematic. Just take one step forward and check what the outputs are. You should beforehand have a good idea of what all your outputs should look like. If you don't know what the outputs should look like, you need to spend a little bit more time analyzing your circuit. Otherwise, you're going to have very little luck trying to debug it. When taking results after we verified that our circuit works as expected, be careful about how you scale the waveforms. For example, here we have 2 fairly good results. You can see in the bottom picture we had to include 2 different waveforms. We didn't want to overlap them, as one of them would simply cover the other one up completely. So we put them on 2 different channels, and we separated them by using our vertical adjustment knobs. Additionally, on the top input here, you can see we wanted to make note of the maximum amplitude of this signal, so we used our scope cursors to outline that on the screen. If we had to make these better, what we could have done is probably expanded the time scale on this top signal. We're not using the whole screen, and we'll get slightly better pictures if we do. Additionally, on this bottom waveform, you can see that this light blue is kind of hard to see, so change the color. It's all fairly common sense stuff, just make sure you're focusing on it. The second set of waveforms, we have a good and a bad here. What we were trying to show was the relationship between this green waveform and the other 2 waveforms. We wanted to show how these things related in time. Now, if you take a look at the top here, we don't care about the purple signal, so why is that still on our scope? We should have removed that, no reason for it to be there. Additionally, we've overlapped this light blue signal with our green signal, making it look fairly messy and hard to see what's what. So we don't like it. Don't add results that look like that. They're confusing and they're just bad. Try and go for what this bottom picture looks like. You see we've separated signals where necessary, and we don't have any signals that we don't care about on there. Fairly common sense, just try and focus on it. If you need to show multiple things about a waveform, it's likely you'll have to include 2 different screenshots. Don't try and mash everything into the same screenshot, because you'll likely just get a worse result. For example, what we wanted to show in this set was the delay between the turn on of the blue signal and when the yellow signal started generating. Additionally, we wanted to show how the yellow signal stopped and if there was any delay between the turn-off of blue and yellow. Now we could have shown this all in one waveform, but we wouldn't have really gotten some nice detail here on the turn-off of yellow. Additionally, we would have just had this thick yellow bar throughout the whole thing. It would have been fairly nasty. So in this case, we decided to go with 2 different screenshots. If you have to, just use 2 screenshots. Don't put one bad screenshot. If you have to take a picture of some of your hardware, add labels and a caption describing what it does. Don't simply put a picture of some random hardware as proof that you've done something. Actually add labels, add a description, make sure you use a nice clean background. Common sense, make it look nice if you're going to put it in a report. So that covers the basics of how we take a breadboard to results. Just make sure in results you're focusing on being clear and clearly showing what you're looking for. When you're troubleshooting, always check signals that you know what they should be first, and then take steps forward from there. Don't jump to your output and call a TA over simply because your output's not what you were expecting. Do some debugging first and ask for help, only if you can't figure it out from there.